Lesson 6 on work, energy, and power. So, what you would do is you would go onto the Google Drive in the folder Lesson 6 under work, energy, and power. And what you would have noticed in there is that there's exercise 2, which is the memo that for the previous lesson, lesson 5, you can mark your work. Any issues, we'll discuss that one on one. And then there's a worksheet that's called Conservative or Cons and Non-Cons Forces Notes, grade 12. You need to print that worksheet, use a highlighter and a pen, and I'm going to go through the worksheet in this video, and then you can take all additional notes to this video. All right, let's have a look here. It starts with mechanical energy, and that's our main aspect of what we're looking at next. It says the law of conservation of energy states that energy cannot be created nor destroyed, but is merely changed from one form into another. So I know that the mechanical energy of an object at a point is the sum of the gravitational potential energy, EP, and the kinetic energy of an object, which we did discuss earlier. So that leads us to two things. One is that I know that I have to have, if I have a system, I must have conservation of energy. And if I have conservation energy, then I know that my mechanical energy at point A, so let's say A and B, my mechanical energy at point A must be equal to my mechanical energy at point B. So I must have that conservation of energy. So when I have, there are two types of forces that exist. The one type of force is called, so I'm just going to do this. You'll add notes to your worksheets. I have something called conservative. Conservative forces lead to conservation. And when I have conservative forces, then my mechanical energy remains constant. So there are forces that exist in the world that will always result in conservation of energy. My other option is non-conservative forces. And those are forces that create a situation where I have no conservation. So those are the two types of forces we're going to look at, and we're going to look at how they affect certain systems. So these formulas here are important to us, all of these. Please highlight them. Make sure we understand that EM stands for mechanical, mechanical energy. EP is my gravitational potential energy. EK is my kinetic energy. M here is for mass. G is for gravitational acceleration. And V over here is velocity. Alright, so that's the bits of information that I have to know. Alright, let's have a look at conservative forces. So when I have conservative forces, they conserve energy. They conserve energy. So let's have a look at my definition. A force is a conservative force if the net work done by the force is 0, while moving an object around a closed path, starting and ending at the same point. So all that means is that a force is conservative if the net work done by the force in a moving object, so you just add notes onto your worksheet, does not depend on the path taken. that means is that when I'm looking at certain forces and I'm not worried about paths that are being taken, I need to think of forces that are natural. So we look at natural forces. So of all the forces you've learned about from grade 9 up to now, we look at forces that just come naturally. So for example, pushing and pulling is not a natural force. So in other words, the gravitational force or weight acts on an object during its motion. The total mechanical energy of the object is conserved. So two things. The first one here, it says that the net work done by the force is zero. In previous videos, we said that perpendicular forces do zero work. So when we talk about perpendicular forces, we're talking about things like Fg or your weight, right? And the normal force, both of which are natural forces. The total mechanical energy of the object does not change if I have these natural forces during the motion. That means it neither gains nor loses mechanical energy. So what that actually means is that all I'm going to have, if it's not gaining or losing, I'm going to have a transfer of mechanical energy. So I'm going to just transfer from one type of mechanical energy to another. So I can go from kinetic energy into potential energy, or I can go from potential energy into kinetic energy. So all the time as the motion happens, if I've only got gravity and I've only got the normal force, then all I'm going to have is transformation or conversion of energy. Not so much energy being added or energy being lost. So if I have an object, so conservative, if I have an object, if an object, and this is an important word, slides, right? If an object slides across, down, or up a slope, across a surface, or down or up a slope, in the absence of external forces, then I'm going to have the only thing acting on it if it slides is gravitational forces or normal forces. So what we mean by external forces can be friction or applied forces, pushes, pulls, engine forces. All of those are external forces that will cause us not to have conservation of energy. So conservative forces, we see here there's a list of conservative forces. Force of gravity, Fg, or your weight. Elastic or spring, electrostatic, buoyancy, and the normal forces. Alright, the normal force, which is Fn. Those are all considered conservative forces. And if I have, what I can say is that if I have only conservative forces, so I can say the total mechanical energy, remember you're adding to your worksheet, the total mechanical energy of an object is conserved only when conservative forces are present. And what we mean is only. So that's why this word slides is so important, is because when something slides, that's it's a natural motion. And we don't have to consider what got it sliding. If it says slides, then I know that I've got only gravitational forces or normal forces, and therefore mechanical energy is conserved. Now, if I had applied forces, then my situation would change. So if I look here on the next thing, it says, suppose a trolley moves down a frictionless inclined plane. So let's look at some of the keywords we're looking at here. It says it moves down a frictionless inclined plane as shown here, and it says ignore air resistance. So all of those things like friction, air resistance, those are all forms of external forces. So when I'm looking at my object, and let's say my object initially was over here. So that's where my object was at the beginning, at point A. And then it went all the way down the slope. And that was its direction of motion. I know that the only way that it got there is due to the force of gravity. So the force of gravity caused the object to move down the slope. Now when that happens, I know that if I'm looking at my free body diagram, I've got Fg over here, and I've got on the surface Fn. So I've got Fg that causes the downward motion, and I've got Fn, which is the support. And if I have an object that does this, I've only got conservative forces acting on the object. What we mean by conservative forces is, and I'm reiterating this over and over again so that we can remember that when we're talking about conservative forces, we're talking about Fg and Fn. So we can say that the total mechanical energy, so we can say therefore the total mechanical energy of the trolley will remain constant throughout the motion along the slope. So I can say that the mechanical energy at point A is equal to the mechanical energy at point B. That's the equation I could use for a situation where I have only conservative forces. I can also, in certain cases, say that if I want work done by conservative forces, that is equal to negative change in EP. Because remember, it only works with gravity. So this is work done by conservative forces is equal to the negative change in potential energy. So that's the second formula that you have available to you. So I can use these equations if it suits the scenario that I'm in. So please make sure you highlight it or something so that you understand what we mean by conservative forces. Right, so the next thing we go into after conservative forces is non-conservative forces. So when we're working with non-conservative forces, it means I'm going to get no conservation of energy. Now, non-conservative forces, they can either they do one of two things. They can either do positive work, and that would mean you add energy, or they can do negative work and it ends up removing energy. Now, if I'm adding any energy or I'm removing any energy, it means I cannot have conservation of energy. So we say that a non-conservative force is one for which work done on the object depends on the path taken by the object. So I can say that a force is non-conservative if the work done by the force causes a change in gravitational potential energy, and the kinetic energy and thus also the mechanical energy. So basically, if I have forces that add energy or remove energy, then I've got a situation where my gravitational potential energy is going to change, my kinetic energy is going to change, and my mechanical energy is going to change. So non-conservative forces, so if I have, let's just highlight this here. If I have non-conservative forces, they will change the total mechanical energy of an object. Alright, so therefore mechanical energy is not conserved. Now let's just have a look at these non-conservative forces. So in this list I've got friction, so force of friction, air resistance, water drag, non-elastic material stress, viscosity, resistance to flow of electric current. Another one is force applied, which is just a basic push or pull, right? I can use force of an engine, and we call that the driving force. So these are all words that come into play when we're working with non-conservative forces. I can also have force of tension or FT, and that is if I use a string of some sort or a rope or cable, right? All of these types of forces, if they act on an object, that is when I've got non-conservative forces. I can even use another one and say a motor force, rocket propulsion, please remember that the minute I see push, pull, driving, engine, tension, string, rope, cable, motor, rocket, friction, those are all non-conservative forces. So we're going to just have a look here at a scenario. Let's have a look here on the next page. Right, I said before, a non-conservative force changes the total mechanical energy of an object. Non-conservative forces are also called dissipative forces, as they dissipate mechanical energy. So friction can dissipate energy as heat and sound. Water drag and air resistance can dissipate energy as a wave or turbulence in a wake. So what we mean by turbulence in a wake is when you have turbulence in an aeroplane. Then you've got situations where you have a non-conservative force. Again, dissipation is a transfer of energy into some form which is less available for doing work. So the thing when we talk about less available for doing work is if we have friction, it gets dissipated as heat or sound. That is how I can remove energy from a system, even knowing that I must conserve energy. All right, so that is what we talk about when we talk about dissipating. All right, well, let's have a look here. Suppose a car, I just want to write those notes down. It says, suppose a car is driving up an inclined plane. So now what we mean by driving, the fact that we said using the word driving means I've got an applied force, right, which is an external force. So the minute I see that, I can see here I've already got a non-conservative force or situation. Right, so I've got a driving force of this engine. Like I said, you can have tension in a cable, an object that is pushed or pulled. Suppose this car is driving up an incline and there's two things happening. There's a force of an engine and there's a force of friction. So I know that friction is a non-conservative force. And the work done by friction is always a negative value. So in essence, when I'm working with friction, I know that it removes energy. I also know it decreases kinetic energy. So that's the one. The other thing that you've got acting on this car is the force of the engine, which is also a non-conservative force. And the type of work that's being done, the work done by force applied is always positive. Which means that if I have the force of the engine, it will add energy or it will increase the kinetic energy, essentially. So even though I look at the system, let's say I did look at the system and I draw free body diagram, I would still have my force of gravity going down, Fg, and going perpendicular to the surface, I'd still have Fn. But remember, even though Fg and Fn are conservative forces, they're not the only forces. So for me to have a conservative situation, I must only have the normal force and gravity. But now I've got the normal force, I've got gravity, I've got an engine force here, and going down my slope, I've also got friction. That means that if I'm driving up a hill, I have got non-conservative forces. So let's have a look here. We can write two statements. If a non-conservative force does positive work, right? And what we mean by positive work, we mean applied forces. In this case, it's upward. The goal is to drive up the hill. Does positive work on an object. Then energy is added to the object. and therefore the total mechanical energy is not conserved. In another instance, if a non-conservative force does negative work on an object. So when we talk about negative work, remember it's always friction. Does negative work on an object, then energy is removed from the object. Right? And therefore the total mechanical energy is not conserved. Right? So let's have a look here at our summary. If a conservative force is the only force acting on an object during its motion, then the mechanical energy of the object is conserved. If the gravitational force is a conservative force. If a non-conservative force acts on an object, then the mechanical energy of that object will not be conserved. Friction will transfer some of the mechanical energy into heat or thermal energy, and we must remember that this is the most important part, is that energy is never destroyed. It must be conserved, essentially. All right, so that is your ideas on conservative forces and non-conservative forces. So how do we get conservation of energy with non-conservative forces? Because remember, the law says that energy is always conserved. But now we see that it's not always the situation. So let's have a look at this example. And what we're going to do is we're going to do a derivation of the conservation of energy using non-conservative forces formula. Okay, I'm going to show you how to work through it so that you have a better understanding of what's happening here. Alright, so suppose we have a trolley and it moves down. So move tells me it slides, but then it tells me it moves down a rough slope from point A, which is here, to point B down here at the bottom. So I've got my initial position at the top of the hill, and naturally, because I've got force of gravity, right, my object is going to want to slide down the slope. That is considered a natural motion. So down the slope. Okay, down the slope is natural. But at the exact same time of having that natural motion, going up the incline, opposing that motion is friction. So friction opposes motion. And I know now that if I have friction, then I have a non-conservative force. Right, so what do I do now? So now if I've got this friction and it's acting on the trolley, what I need to understand is when I'm looking at my situation here, point A and point B, and as this object slides down, I need to realize that the as I go down, as this trolley goes down the slope, it starts off with a lot of energy. But because of friction, it loses some energy. So I know it's losing energy because friction is a non-conservative force which removes energy. Alright, so if I'm looking here, I can say that because I have friction, because of the presence of friction in the setup, the mechanical energy of the trolley at point A is not equal to the mechanical energy at point B. That's the first thing I need to recognize. So I can have a formula that says the mechanical energy at A is not equal to the mechanical energy at point B. So if I'm looking at friction and I know that I've got a non-conservative force, I know that the friction does negative work on the object. All right, it does negative work on the object, and that means that some energy is dissipated to the surroundings. So if I think of going down a hill with a car and now I've got a lot of friction, my wheels are going to get really, really, really warm. So that means I have a significant loss of energy. All right. Now when friction acts on the trolley, your initial, so let's get that down. Your initial, when friction acts on the object, the initial mechanical energy at A is greater than the final mechanical energy at B. So then I can say that the EM, or the mechanical energy at A, is greater than the mechanical energy at point B. So I can say that the sum of the gravitational potential energy at A plus and the kinetic energy at point A is greater than the sum of the potential energy at point B plus the potential energy at point the kinetic energy at point B. So when I'm looking at that, that's my basic setup of what's going on now. So let's say, let the work done by non-conservative forces be WNC. WNC. So that means, therefore, the negative work done by the non-conservative forces WNC is equal to the energy dissipated to the surroundings. Now I know, and the statement that we're working with is that energy is always conserved. Now, if energy is always conserved, we need to include, we must include the work done by all non-conservative forces. Right? Like friction in this instance, or an engine force. Right? So because we either add energy or remove energy, right, we're going to end up with a formula that reads potential energy at point A plus the kinetic energy at point A plus work done by all non-conservative forces should be equal to the potential energy at point B plus the potential energy at the kinetic energy at point B. So this means that if I must include this work non-conservative, this equation says that therefore I'll have conservation of energy, because I'm taking into consideration here that we either add or remove. Let's get that in a better place rather. We add or remove energy. So we adding or removing it. So if I wanted an equation for work done by non-conservative forces, I can just rearrange my formula and say work done by non-conservative forces is the potential energy at point B plus the kinetic energy at point B minus the potential energy at point A minus the kinetic energy at point A. So looking at that kind of situation, I've got work non-conservative is equal to my EP at point B minus my EP at point A plus my EK at point B minus my EK at point A. And that can all be simplified into a formula saying that work non-conservative is equal to the change in EP plus a change in EK. And that is your formula for work done by non-conservative forces. We have to take the non-conservative forces into consideration. So on your left hand side here, you have work done by all non-conservative forces. What that means by saying all non-conservative forces is that I can look at W net. You can choose method 1 or method 2, but this WNC refers to everything. So if I had just friction, then I would have W friction. If I had W force applied, then I would have W force applied. But if I had both, then I'd have to work out the net work being done. On the right hand side of your equation, so right hand side, I've got the sum of the change in gravitational potential energy which is my EP of the object, and the change in kinetic energy, my EK of the object. So this formula is your main formula. And from this formula, so let's not forget that this here, oops, is your left-hand side. The other side is your right-hand side, and we can say that this formula says the work done by all non-conservative forces is equal to the change in the total mechanical energy of the system. Right? And all we're looking at here is another form of the work energy theorem. All right. So that's your whole thing on work non-conservative or conservative forces. Let's have a look at, I'll go through a little summary. So this is the last little bit, and I'm just going to add a bit of notes to this. What I can see is that the mechanical energy of a system is conserved when only conservative forces are present in the system, like the gravitational force, right? And we can see this in terms of momentum as well, vertical projectile motion, or whatever the case is. We also know that it means that the mechanical energy at A is equal to the mechanical energy at B. So what we mean by at A, we mean initial. And what we mean at point B, we mean final. So you will see the formula looking at point A and point B. We can use initial, final. That's a little bit of a better way. I've only been using A and B because we had an example that we looked at. So you could say that your mechanical energy initial must equal to your mechanical energy final. And everything will be referred to in initial, final, and so on. So when I'm looking at these kinds of forces, or these conservative forces, then I'm going to have conservation of energy. The mechanical energy of a system is not conserved when non-conservative forces are present in the system. Friction, air resistance, applied forces, tension, and so on. The work done by these non-conservative forces, WNC, is equal to the change in the total mechanical energy of the system. That gives me this formula of WNC is equal to the change in EP plus the change in EK. So how that actually looks is, I can say W net is equal to MGH final minus MGH initial plus half MV squared final minus half MV squared initial. That is the main formula. That's where you get a mark. But this formula here is where we're going to do all of our substitution, which means I can use this formula to find things like gravitational acceleration, mass, height, final velocities, initial velocities. This W net here is the sum of all non-conservative forces. Alright, so this is a lot of theory to work through. Normally I would give you an exercise, but instead of an exercise, we're going to do example 16, example 17, and then we're going to go. You will do the calculations for example 16, 17, on to example 18 over here, and the video example 19. But what I am going to do is, you'll see that this video is called Work, Energy and Power Lesson 6 1. You're going to go to Work, Energy and Power Lesson 6 2. And in that 18 and 19, which you can just cut out and paste and then do all the calculations underneath. So I'm going to work through every single one of these with you so you have some sort of guidance rather than doing it by yourself and getting lost. If you are feeling confident, you're more than welcome to do it by yourself and then watch the next video and see if you were correct or not. But it is a little bit more complex. So take your time in getting through all of that.